Okay, are there any questions at all from anything we did last time? All right, so today what I want to cover is section 11.3, and I will be doing my best to actually finish it. So this section 11.3, the homework would be from 9 to 29, the odd problems from the text, but I also have web assigned problems very similar to this ones. And so if you do the problems in web assignment, you should be fine, but if you want more practice, you could also look at those problems. All right, so what's the integral test? So from now on, you'll see a lot of tests. Okay, what are these tests? Well, these are tests for convergence of a given series. So a lot of the times, for a given series, you cannot find the exact sum, but you still need to know whether the series is convergent or divergent. And if the series is convergent, then you can approximate the sum of the series by just looking at, let's say, the first 100 terms. Am I making sense? So what's the integral test? Well, let's let f of x be a continuous, positive, and decreasing function on the interval from m to infinity, where for simplicity I'm assuming m is an integer. Number one, if the improper integral of f from m to infinity is convergent, then the associated series k going from m to infinity of f of k is also convergent. Okay? And number two says if the improper integral of f from m to infinity is divergent, then the associated series k going from m to infinity of f of k is divergent as well. Is everybody okay? Let me try to give you a justification of 1 and 2. It's not going to be a formal proof, but just a justification why 1 and 2 should be true. So let's think about the graph of f. F is, remember, continuous, positive, decreasing. So the graph of f should look like what I have in my two figures. First of all, concentrate on the first figure. Remember, number one says what? Number one says if the improper integral of f from m to infinity is convergent, then the series summation k going from 1 to infinity of f of k is convergent. So let's see why that should be true. How am I going to associate? How am I going to associate the series with the integral? Well, this is how I can do it. Look at the graph of f. Look at the region below the graph of f. Let's assume that the improper integral of f from m to infinity is convergent. In the first figure, I am assuming that the improper integral of f from m to infinity is convergent. Okay? That's my assumption. So I am assuming that this guy is convergent. What does it mean graphically? What does it mean graphically? Graphically, yeah? I mean, the improper integral is convergent means that the improper integral is a number, right? It's not necessarily zero. But in terms of the graph, what does it mean? When you integrate a function, it gives you what? if you're integrating a positive function, it gives you the area below the graph, right? So what area is represented by the improper integral? The improper integral m to infinity represents the area below the graph of f from m to infinity, right? So what we are saying is that infinite region, it has finite area, right? So if I assume that the improper integral of f from m to infinity is convergent, it means that the area below the graph of f from m to infinity is a finite area. Okay? All right. Now, the interval from m to infinity, I am going to divide it into subintervals of length 1. So m to m plus 1 to m plus 2 to m plus 3 and so on. Is everybody okay? The interval from m to infinity is being divided into subintervals of length 1. So on the first subinterval, I have a rectangle where the height of the rectangle is the same as the height of the graph of f at the right-hand point m plus 1. Right? On the second subinterval, I have a rectangle where the height of the rectangle is the same as the height of the graph of f at m plus 2. Right? What's the total area of this rectangle? So on each subinterval, I am making a rectangle, and the height of each rectangle is the same as the height of the graph at the right end point of the subinterval. What's the total area of the rectangles then? Well, what's the area of the first rectangle? The width are all 1, so the area of each rectangle is the same as the height of the rectangle. So what's the area of the first rectangle? Well, f of m plus 1. What's the area of the second rectangle? F of m plus 2. And so on. So what am I getting then? I'm getting f of m plus 1 plus f of m plus 2 plus f of m plus 3 plus dot dot dot, right? So this is what? This sum that I have here, this is an infinite sum, right? This is the total area of the rectangles. Is everybody okay? That's the total area of the rectangles, and that's got to be less than the area below the graph, right? Well, what I'm doing next is that on both sides of the inequality, I am adding f of m. So first of all, I am writing the sum f of m plus 1 plus f of m plus 2 dot dot dot, that infinite sum with summation notation, k going from m plus 1 to infinity, f of m plus 1, f of k. It should be f of k. Sorry. Let me make it. There is a typo here. This should be f of k. Okay? So k going from m plus 1 to infinity, right? That's the left-hand side. The right-hand side is still the integral from m to infinity. Now, on both sides of this inequality, I'm adding f of m. So if I am adding f of m on the left-hand side, I'm getting the sum k going from m to infinity of f of k. On the right-hand side, I get f of n plus the integral. Now, since we are assuming that the integral is convergent, right? The integral, this guy we are assuming is convergent, right? If that is convergent, then it implies that the infinite series, summation k going from m to infinity of f of k, should also be convergent. Why? Because that series is smaller than the integral. Right? Is that making sense? For that series, f of m plus the integral is an upper bound. So if the integral is finite, then the series should be finite as well. Or convergent, I mean. Is that making sense? This is not a formal proof, by the way, but it's just giving you an idea why the series should be convergent when you know that the integral is convergent. Is everybody okay? So if the integral is convergent, then the series is convergent. Now do the opposite. Now look at the second statement. The second statement said what? And if the integral is divergent, then the series is divergent. Let's see why. Now look at the second figure. In the second figure, I am now assuming that the integral that I have here, m to infinity of f is divergent. The integral of f from m to infinity is divergent. That's what I'm assuming. What does it mean in terms of the graph? In terms of the graph, it means that the area below the graph of f from m to infinity has infinite area, right? It doesn't have finite area anymore. So when the improper integral of f from m to infinity is divergent, it means that the area below the graph of f from m to infinity has infinite area. Okay. Now let's do the same thing. We have the interval from m to infinity divided into subintervals, where the length of each subinterval is 1. So you have m plus 1, m plus 2, m plus 3, and so on. And on each subinterval now, you're going to make a rectangle, but the height of the rectangle will be the same as the height of the graph at the left end point of the subinterval, right? So now you're going to get this rectangle. So what's the area of the first rectangle? The area of the first rectangle would be f of m, same as the height. Area of the second rectangle would be f of m plus 1, and so on. So I am getting the sum f of m plus f of m plus 1 plus f of m plus 2 plus da da da. And if I write it in summation notation, I get the summation k going from m to infinity of f of I have a typo again here. This should be f of k. This should be f of k, which is greater than or equal to the improper integral of f from m to infinity. Now remember, we are assuming here what? We are assuming here that the integral is divergent, right? Which means the integral is divergent means what? The value, so if I look at, instead of infinity, right, here, if I put t here, and if I look at the integral from m to t of f, then what we are saying is that as t goes to infinity, the integral goes to infinity, right? So that would mean that the series must be divergent as well, right? If you look at the partial sums of the series, the partial sums are going to infinity. Is everybody okay? Yeah.
So why do you how do you decide to connect the rectangle from the right corner out of the left corner?
Yeah, depending on whether the integral is convergent or divergent. So if the integral is convergent, then if the integral is convergent, then I want to show my series is smaller than that, so that the series would be convergent, right? If the integral is divergent, then I want to show that my series is bigger than the integral. Because the integral is divergent, then the series, because it's bigger than the integral, it should be divergent as well. So whether I'm going to use the rectangles, I'm going to use the heights, smaller heights or the bigger heights, depends on whether the integral is convergent or divergent.
Like what if you connected on the convergent one connected on the left side? Wouldn't it still converge, just be a little bit bigger?
No, because okay, so suppose that on this figure, right, you're saying on this figure, let's say I use these rectangles, right? If I use these rectangles, then what's going to happen? Well, then this inequality would be bigger than, right? Well, what's going to happen then? Then I'm saying basically, oops. Okay, I don't know why. Okay, so this would be greater than or equal to here as well, right? But what you're saying is your series is bigger than a convergent series, right? But does that necessarily imply that your series should be convergent? Because all you're saying, your series is bigger than that convergent integral. But that doesn't necessarily say that the series is convergent, because it's bigger. You know it's bigger, but it may be a lot bigger, so it may be divergent, right? Am I making sense? So it depends on whether the integral is convergent or divergent. If the integral is convergent, then you want to show your series is less than, then you can make a conclusion. Otherwise, you cannot make a conclusion out of it. All right. So let's see with an example how we are going to implement this integral test. First of all, let me look at an easy example. So let's say I have the series n going from 1 to infinity of 1 over n squared, and I want to decide lots of problems till section 11.6 would be about given a series, is it convergent or divergent? Okay, lots of problems like that. So is this convergent or divergent? Well, let's see. First of all, let us associate the terms of the series with a function. So let's take f of x to be 1 over x squared. Well, then clearly f of n would be 1 over n squared. And for any n bigger than 1. So that means that my series is the same as what? My series is the same as n going from 1 to infinity of f of n, right? My series is the same as this series n going from 1 to infinity of f of n. Is everybody clear? Now notice f of x. Is f of x continuous? Is f of x continuous? From 1 to infinity? It's not continuous at 0. But from 1 to infinity, is it continuous? Right? Is it positive from 1 to infinity? Right? Is it decreasing from 1 to infinity? Right? So I can apply integral tests, right? It's got to be continuous, f has to be positive and decreasing. All those are satisfied here from 1 to infinity. So the integral test applies here, right? So what does the integral test says here? Integral test says that the series n going from 1 to infinity of f of n, whether that series is convergent or divergent, depends on the integral from 1 to infinity of f of x dx. In fact, you don't have to start the integral at 1. You can start the integral at whatever number you want. Am I making sense? But here I'm going to start at 1. So if this integral is convergent, then the series will be convergent. If the integral is divergent, then the series is divergent as well. So basically, then I have to come up with whether the integral is convergent or divergent. If I know that, I know whether the series is convergent or divergent. So let's see. Let me go there in a second. I'll show you the picture in a second. So let's look at the integral from 1 to infinity. Remember, this is f of x, right? This is my f of x. So let's look at that integral. What is that integral? Well, improper integral, how did we define them? I have infinity as the upper limit. Replace that with the parameter t, and then take the limit as t goes to infinity. So you're looking at the integral from 1 to t, 1 over x squared dx. What's the antiderivative of 1 over x squared? What's the antiderivative of 1 over x squared? You're talking about 1 over x. Log x is the antiderivative of 1 over x, right? So we have 1 over x squared. Yeah, 1 over x squared is the same as x to the negative 2, right? So by the power rule, x to the negative 2 has antiderivative what? X to the negative 2 plus 1 divided by negative 2 plus 1, right? The antiderivative would be x to the negative 2. That's the integrand. So the antiderivative would be x to the negative 2 plus 1 divided by negative 2 plus 1, right? And that's exactly negative 1 over x. Okay, so once I got that, now I'm going to plug in t, plug in 1, and then subtract, right? If I do that, I get what I have within the brackets. And then I'm going to take the limit as t goes to infinity. And the limit as t goes to infinity, 1 over t goes to 0, so I end up with 1. So that tells me that the improper integral is convergent. Because the improper integral is convergent, then I know that the associated series n going from 1 to infinity of 1 over n squared is also convergent by the integral test. Is that making sense? Any questions on that? Okay, a lot more engagement from you is needed in this chapter. Okay, this chapter is a little bit more abstract than the other chapters, so you need to be more engaged in this. So let me show you a picture of this problem. That is what's going on here. You see the graph of 1 over x squared, right? You look at the graph of 1 over x squared. Let me delete the number 1 for now. If you look at the graph of 1 over x squared, forget about the first rectangle, okay? Forget about the first rectangle. Just look at the rectangles from 1 up to infinity. So what am I doing here? I know if I look at the integral from 1 to infinity of 1 over x squared dx, that's finite, right? This guy is finite. This is equal to 1, right? We saw that. Which means that the area below the graph of 1 over x from 1 to infinity is finite. I have finite area below the graph from 1 to infinity. So look at the rectangles where the heights are taken to be the heights at the right end points. So then the first rectangle has area 1 over 2 squared, right? What's the height at 2? The height at 2 is 1 over 2 squared because the function is 1 over x squared. What's the height at 3? 1 over 3 squared. What's the height at 4? 1 over 4 squared. So if I add the total area of the rectangles, I'm going to get 1 over half squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so on. So now I'm going to add 1 on both sides as well. So I can see that the series, remember, let me write in black, that this is the, so what is this series here? This is the series n going from 1 to infinity of 1 over n squared, right? That's what I have here. And on the right hand side I have 1 plus the integral, right? So if the integral is convergent, then the sum series would be convergent. So in picture that's how it looks like. You don't need that picture for the solution, by the way. Okay? I'm just showing you how it looks like in picture. Let's look at another example, and this time I'm going to go over it. Yeah.
So that last one converged to 1.
Well, we know that the series is convergent, but we don't know whether the series converges to 1.
And what was the 1?
1 was the value of the improper integral. So we showed that the improper integral converges to 1, but the improper integral is only an upper bound for the series. So we know that the series is bounded above by the integral, but that doesn't mean that the value of the series is the same as the value of the integral. Am I making sense? The value of the series is less than the value of the integral. That's all we know. We don't know the exact value of the series, right? The exact sum of the series is not known.
So it looks like it'll be greater than 1. If you're adding up 1 plus 1 plus 1.
Yes. Oh, by the way, that's why I'm saying this is actually 2, right? It's greater than 1. You're right. The value of the series is greater than 1. It's in fact the value of this series is pi squared over 6. Okay. However, it is less than 2 because the integral, remember, was 1, but I have that extra 1 there. It's less than 2. So all I know is that the series is less than 2. Right. So you're right. The series has value bigger than 1. But all we are saying at this stage is less than 2. Now, the exact value of the series is in fact pi squared over 6. However, we're not going to go over that because it's a little bit hard to come up with that. Okay? So, the question was whether the series is convergent or divergent. And our answer is that the series is convergent. That's all. All right. Any other questions? Let's go over this problem. In this problem, you have this series here. Now, first of all, if I want to apply the integral test, I have to look at the associated function. Let's say f of x is 1 over root x, and I'm going to take this function for x bigger than or equal to 1. So we are letting f of x to be this function. Now notice then I could say that f of n is 1 over root n, right, clearly? And this is for any n bigger than 1. So that means the series that I have in hand, 1 up to infinity, 1 over root n, this series is the same as the series n going from 1 up to infinity of f of n. So now think about the function f. The function f is it continuous? Is it positive? Is it decreasing for x larger than or equal to 1? The answer is yes. The function f is continuous, positive, and decreasing for x bigger than 1. So then, by integral test, what do we know? By integral test, whether this series is convergent or divergent, right? By integral test, this series is convergent or divergent according as the improper integral 1 to infinity of 1 over root x dx is convergent or divergent, right? Is everybody clear? So in order to determine whether the series is convergent or divergent, all I have to look at is whether that improper integral is convergent or divergent. So what do I do? Well, I just compute that integral. So what's the integral from 1 to infinity of 1 over root x dx? Well, I take the limit as t goes to infinity, integral from 1 to t, 1 over root x dx. Okay, what's the antiderivative of 1 over root x? Anybody? What's the integral of 1 over root x? 1 over root x is what? It's x to the negative half, so the integral would be x to the negative half plus 1 over negative half plus 1, right? So if you simplify that, what do you get? Do I get 2 times root x? You agree with that? Right, x to the half, and then I have a half in the denominator, so that's going to become a 2. And then I am going to plug in t and 1. So I do that. If I do that, I get this. And now it's clear that the limit is what? It's clear that the limit is, well, the limit of root of t is what? As t goes to infinity. That negative one doesn't matter, right? So I get half. I get infinity. So that means that the integral from 1 to infinity of 1 over root x dx is divergent, right? So by the integral test, then the series 1 over root n going from 1 up to infinity is divergent as well. Is everybody okay? Everybody's okay? So once again, you don't need to look at the graph of 1 over root x, but I'm going to show you what's going on in the graph. If I look at the graph of 1 over root x, because the integral from 1 to infinity of 1 over root x is convergent, it means that the area below the graph of 1 over root x from 1 to infinity is finite. And the series that we have in hand, you can think of the series, the sum of the series, as the total area of the rectangles that I drew. If you look at the total area of the rectangles I drew, that's exactly our series. And that's bigger than the improper integral. So from here I know that the series 1 over root n as n goes from 1 to infinity is larger than the integral from 1 to infinity of 1 over root x dx. So because this guy is divergent, we know that the series is divergent. Okay? So that's all we did. Is everybody okay? Yeah.
So on our website, if we find it to be convergent, isn't it going to ask us what it converges to?
No, it's not going to ask you what's the sum of the series. Is that what you're saying?
Yeah.
The only time you're going to be asked to find the sum of the series if you have either a geometric series or a telescoping series that we saw last time. How to find the exact sum. Yeah, those are the nice series for which we know exactly how to find the sum. Now, p-series. A p-series is a series of the form summation n going from 1 to infinity of 1 over n to the p. Now, p is a constant there. It's called a p-series. And the next theorem that I'm giving you is called the p-series test. You can prove this by using the integral test, which I'm not going to do. I gave you two examples, right? One where p is what? In my first example, what was p? 2. In my second example, p was half, right? Now, my theorem p-series test says that the p-series is convergent if p is larger than 1, and it is divergent if p is less than or equal to 1. And you can use the integral test to show why that's the case. Okay, I won't do that. In your homework, there is a homework where it sort of goes through the steps. You just have to follow the steps. Okay, and you can use this p-series test in your homework. That is, if you're given if you see that you have a problem where the series is 1 over n to the 10, you can right away say that it's got to be convergent by p-series test. Okay. For example, let's say I have the series n going from 1 to infinity of 1 over n to the 5/6. Is this convergent or divergent? I don't have to do any work. I'm just going to say by the p-series test, it is divergent because p is 5/6 is less than 1. Okay? And then in the other example where I have the summation n going from 1 to infinity of 1 over n cubed, that's convergent by the p-series test because p here is 3, which is bigger than 1. Is everybody clear how to use the p-series test? Is that okay? All right. Now let's look at a little bit more difficult use of the integral test. It's not difficult, but it's just that it's not clear whether the function f is increasing or decreasing in this case. So let's say I have this series. Summation n going from 1 to infinity of ln of n over n. I want to know whether this series is convergent or divergent. Now, by the way, I want to make a point here though, even if I have to show this series is convergent or divergent, right? Let's say instead I show that the series from 10 to infinity of ln of n over n is divergent, right? Would that also imply that, or convergent? Let's say I show that this series is convergent or divergent, whatever I show. If I start at 1, can I still make the same conclusion? The answer is yes. For finitely many terms of a series does not determine the convergence. The convergence is not determined by only finitely many terms. So even if you get rid of finitely many terms, you still get the same answer, convergent or divergent. Am I making sense? But okay, let's start at 1. Okay, so we're going to look at f of x, which is ln of x over x, and let x be greater than or equal to 1. Now we need to know whether f is what? Continuous? Well, is it continuous? Yes, because when x is bigger than 1, numerator and the denominator, both of them are continuous, and the ratio, the denominator doesn't vanish when x is bigger than 1, right? So it's fine, continuous. is it positive? Well, that's a little, you have to know the log function very well. ln of x, is it positive? Well, remember the graph of ln of x. ln of 1 is 0. ln of x is increasing. So ln of 1 is 0. That means ln of x for any x bigger than 1 would be positive. So ln of x is positive when x is bigger than 1, right? Am I right? Okay. So I know that f is positive. Now the third question is, if f is f decreasing? Well, it should be, but it's not so clear that it is decreasing. So I have to do some work. So let's see. Well, how do I find out where f is decreasing? Well, take the derivative and see where it's negative. So take the derivative here. If you take the derivative of f by using the quotient rule, you are going to get 1 minus ln of x over x squared. I didn't show you the details here, but you just use the quotient rule. The derivative will be simplified to 1 minus ln of x over x squared. Now you ask yourself, when is this derivative negative, right? Because you want to know when f is decreasing, right? Where f is decreasing. Well, in order to do that, you need to know where the derivative is negative. Now, this derivative is negative when? This derivative is negative when the ratio is negative, but the denominator is already positive, right? X squared. X squared is already positive. So whether the derivative is negative or not depends on the numerator. Look at the numerator, 1 minus ln of x. When is this negative? When is this guy negative? The numerator. Well, the numerator is negative when ln of x is bigger than 1, right? If ln of x is bigger than 1, then the numerator would be negative. Well, now ask yourself, when is ln of x bigger than 1? Well, remember ln of e is 1. ln of e is 1. So ln of x is bigger than 1 when x is bigger than e. When x is bigger than e, ln of x would be bigger than 1. So that's exactly where the derivative would be negative. The derivative would be negative when when x is bigger than e. E is about 2.7 something, right? E is about 2.7 something. Okay? So we know that the function f is not decreasing from 1 to infinity. It is only decreasing from e to infinity. So let me just say then that the function f is decreasing on 3 to infinity. It's actually decreasing from e to infinity, but 3 is bigger than e, so I can say it's decreasing from 3 to infinity. Right? I didn't have to say that, but I'm just telling you that I can start at an integer bigger than e. So by the integral test, then what do I know? By the integral test, my given series was what? My given series is n going from 1 to infinity of ln of n over n, right? Now, what's the first term of the series? What is the first term of the series when n is 1? 0. So that's 0. I can just get rid of that. When n is 2, what's the term? ln of 2 over 2, right? And then I kept the rest of, so I took out the first two terms, and then I have the remaining series, n going from 3 to infinity of ln of n over n. So my given series is convergent as long as, so this guy is convergent as long as this guy is convergent, right? Right? Or this guy is divergent if this guy is divergent, right? Am I making sense? So if you know that the series starting from 3 is divergent or convergent, then you know the series starting at 1 would also be the same. Am I making sense? So if the series n going from 3 to infinity of ln of n over n is convergent, then our given series is convergent. If the series n going from 3 to infinity of ln of n is divergent, then our series is divergent as well. So, but for this series though, I can apply integral test. How? Because now I know that for this series, this series is this series is convergent or divergent according as this guy is convergent or divergent, the integral from 3 to infinity of ln of x over x dx. If that is convergent, then the series is convergent, otherwise divergent, right? Yeah.
So we found starting at n equals 3, it starts decreasing.
Yeah, that's right. Yeah. Yeah. Okay, well, I'm actually making a fuss here. Actually, as long as the function f is decreasing after some point on, you can just see whether the integral of f is convergent or divergent from that point on. As long as that's convergent, your series will be convergent, in fact. So you don't need to make any fuss about starting at 3, in fact. So what I'm going to do now is look at the integral of ln of x over x. Instead of going from 3 to infinity, I'm going to go from e to infinity. Okay, why? The integrand is positive, right? So it does. If I start a little bit earlier, the lower limit, it's even better, right? So why am I using e and not 3? I could have used 3. I'm using e because it's ln of e is 1, ln of 3 is, I don't know. Use the calculator, right? So I'm going to use e. So ln of x over x, integral of that, what is that? Well, limit t goes to infinity, e to t, ln of x over x. How do I integrate that? How do I integrate that? Well, I have to use the substitution. You take u to be ln of x, and then du would be 1 over x dx. Okay? So if I do that, my integrand will become u du. My integrand will be u du. What are the limits of integration for when you change the variable? Well, when x is e, what can you say about u? When x is e, let's look at here. When x is e, what is u? 1. U is 1. When x is t, u is ln of t. So that's what I have. So now what's the antiderivative of u? Antiderivative of u is u squared divided by 2. Now you're going to plug in ln of t and 1. If you do that, you get half ln of t squared minus half. And then as t goes to infinity, what is that? Infinity. Okay? So that implies that the integral from e to infinity of ln of x over x is divergent. And so the series n going from 1 to infinity of ln of n is divergent by the integral test. So why was this problem a little bit complicated? Because we needed to show that the function f was decreasing indeed. We needed to check that. Because looking at the function f, it wasn't clear. I mean, if you have 1 over x squared or 1 over x cubed, it's obvious that it's decreasing. But in this case, it wasn't so obvious. So we had to do that. And also, another point I wanted to make here is that even though originally in the integral test, we are saying m going from the starting point for the series m, and the starting point, the lower limit for the integral is also m. It doesn't have to be m here. Okay, these two m's don't have to be the same. If they are a little bit different, that's fine. Am I making sense? Is everybody okay? Why they don't have to be the same? Because again, the convergence of a series does not depend on first few terms. Okay, even if you get rid of them or change them, it doesn't change the convergence of the series. Okay, any questions on the last example that we did? Any questions at all? No? Okay, I'm going to end here, but we are not really done with this section, so let me put a mark here that we got done here. And I'm going to finish the rest tomorrow.